In this video, we're going to take a look at uncertainty and cost estimation because of some of the discussions we've been having in this last mod here. So I'm going to try to do this quickly. This is a cost estimate. It was prepared by the Baltimore District for a small ecosystem restoration project some years back. I don't want to spend time describing the project, so let me just begin here in column A and say these are the design features. This has armor stone and riprap and core stone and filter stone, and all these different design components. And in column B, we have the quantity for each of these components, the units of measurement, and then the unit cost for each of these components, as well as their units of measurement. And then the total cost is quite simply just the quantity times the cost to get the total cost. And if we scroll on down, you can see the details of this project. And what we're interested in, of course, down here is this number, which is very precise, $7,288,495, and it is also very wrong. And the reason it's wrong is because we don't know exactly what the quantity that will be excavated and loaded is, and we don't know what it's going to cost. So how do we deal with that? We would deal with that in an honest way. And what we were doing, and this was many years ago, this could have been 20 years ago, I honestly don't remember. We went to the district and found out their most likely estimate, the number that they were using for excavation and loading, was 33,000 cubic yards. So when we spoke to those folks about would you be surprised if it was a little more or a little less, of course they wouldn't. And in fact, they said this number could actually be plus or minus 10%. And so that's what we define here. 10% less means it could be 29,700. 10% more means it could be as high as 36,300. And if we take a look down through all of these different quantities and then the unit cost, we see the same thing has been done. And let's pick the unit cost for this. The most likely number was $1.28. The district folks said, I don't see it being much less, maybe a penny, could be $1.27. But when we said, could it be higher? They said, well, yes, it could. And you'll notice there's an asymmetry here. It could be a penny less, but it could be 19 cents more. But for whatever reasons, they were choosing $1.28, and I think we know those reasons. That was the pressure to keep the costs down. This was a continuing authority project, and it was very important that the bottom line cost be low. It's also very important that the bottom line cost be accurate, but that's a story for another day, perhaps. So when we come over here, what I would like you to see is this. This is that value, excavation and loading cost, and it says $1.28, and this says 33,308. That's a very precise number. But here's how we deal with the uncertainty. What is really in that cell is an uncertain number. This is a triangular distribution. It says, imagine we're looking on the number line, and what we're trying to say here is, tell me what numbers are possible. And so we say, okay, it's not going to be less than $1.27. It's not going to be more than $1.47. And do you know anything else? Yes, $1.28. That's the most likely value. And so we grab that value and we lift it up. We exalt it above all other values here. So I have three values now, and I have a ruler. So I'm going to connect those three values, and we have a triangular distribution. Now, what's this telling us? It's saying, the shape is saying, numbers here in the fat part of the graph are more likely than numbers out here. So what do we mean when we say that? Let's close this up now and take a look at this number, because I'm going to be hitting my recalculate button, F9. Now, it could be $1.38. It could be $1.30, $1.34, $1.33. Could be all these numbers. You'll notice that we don't get big numbers like $1.48 too often. You see a lot of 30s and such. So what happens is every time I calculate this, the computer is randomly grabbing a number from that distribution and inserting it into this spreadsheet model. It's doing the same thing over here for quantities. Each one of these blue numbers, in fact, is a distribution. Some are symmetrical like this one, some are not like the others. Okay, so when it plugs numbers in, of course, there's just simple mathematics, multiplication, and then a bunch of addition. And so down here, we are estimating what the cost of this project could be. And the answer is, I don't know. It could be this, it could be that, it could be this or that, or this or that, or this or that. And so this is how we would build a cost estimate from the bottom up. This is different than the way Walla Walla does it. We are basically saying these design elements over here, the quantities of each of these and the cost of each of these is unknown. And we begin with a distribution and build the cost as you've seen here. What Walla Walla does is they take the best cost estimate, and that's done the old style. Go to M. Casey's M2 and come up with the best estimate of the quantity and the best estimate of the cost. And so they come up with a baseline cost estimate. And then they would look at variations from that. But let's see how this works and what we can do with it. Here is our output that we're going to be interested in. We're going to do 10,000 iterations real quick here, or take a moment or so. So what the computer is doing is it's doing a lot of what if. What if this quantity is high and that cost is low? And what if this quantity is high and that cost is high? And all of these things are happening, and you begin to see our distribution of cost taking shape. And this is why we say there's no such thing as the number. Okay, there is no such thing as the number. What we have here is a distribution of total costs. And let's suppose, just for convenience, that this was a continuing authority program that had a cap number of 7 million, just because that's convenient for our example here. I pull my delimiter over to this, and it says 29.2% or 2,920 of my 10,000 iterations produced cost estimates in excess of a $7 million cost. Look down here at this cost rate now. This is $7,290,000, so that's a good example of a cost over $7 million. But if we were trying to decide, do we do this project, do we put it in under the CAP program, this is saying, well, there's a 29.2% chance that the cost is going to blow, that you're going to exceed the limit for this program. So this is where you have to be a risk manager. Are you willing to roll the dice on that? So that's one way that we would use these numbers. Here's another way. Suppose we said, I've got all these different costs from, look up here on this table, from 5.8 million to 7.9 million. The cost is in there somewhere. And oh, by the way, if I scroll down, I could easily grab my 5-number summary from this stuff. But that's not our goal today. The best estimate, the mean, is 6.8. But if I use 6.8, let me put 6.8 in there. Suppose I use the mean cost, 6.8. Well, wow, there's a 56.5% chance that we're going to exceed that in reality. And that's not an acceptable risk. So suppose I work over here and say, well, I'm the risk manager. I'm willing to live with a 10% chance of an overrun. Well, if you're willing to live with this 10% chance, then the cost you're going to go forward with is $7,194,000, because there's only a 10% chance that the actual cost will exceed that. If my estimates, if my uncertainty about the quantities and the unit cost is reasonable. And if you said, well, I'm a little bit more of a risk taker than you are, and you might say, I want 20%. Well, then you would use a lower cost estimate. You'd say $7,081,000. Okay? So there are many ways that we can use this information to our advantage. If I put a 5% in here, I can now say, notice this 90% here? This is a 90% confidence band. I'm 90% sure that the true cost is going to be somewhere between 6.3 and $7.3 million. So this is why I'm telling you that, to be honest, we got to start saying, I don't know the number. And we can't report one number for a cost estimate. You know, what's interesting to me is Walla Walla does some good cost risk assessment. I might differ in what I would like to see them do, but they are doing what the industry does. But we still use one number, and that drives me nuts.